action. So I should start with a thanks to Kurt when he invited me. Of course, I was very happy to come. He told me that this was a seminar series on gravitational wave research broadly interpreted. And I feel we're going to be making this broad as it's ever been here. So I'm sorry about that if that doesn't quite fit the agenda. But what I did want to do is talk about something that I think is extremely interesting, where there's a lot of new progress and hopefully a lot more to come. And so hopefully, even if it's not directly applicable to gravitational waves, it's something you'll be interested in hearing about. Okay, so the talk, of course, starts when we want to understand our universe. And I just put this plot up here. But of course, here at Caltech, I'm probably one of the last people who should talk about it. So you all know what the plot says. And it says that we have dark matter, dark energy, and baryons, and a tiny little bit of neutrinos. And the really interesting thing is, of course, that the precision is much smaller than it used to be. It's remarkable precision. And we know, for example, in the case of dark matter, almost exactly how much of it there is. And, of course, there are remarkable results, particularly the fact that there is dark energy. Okay. So this is spectacular progress. I would even call it a revolution in the last few years. But as any good revolution does, it opens up a whole bunch of new questions. And so just because we know how much of it there is, it doesn't mean we've done. There's a whole bunch of questions. So for dark matter, probably the first question is it a fundamental particle? And I will assume that it is throughout this hour. But that would be a good starting place. Once you assume that it's a fundamental particle, then the question is, what are its properties? What is its mass? What is its spin? How does it interact? Does it have weak interactions, strong interactions, etc.? Is it absolutely stable or just very, very long-lived? And of course, we really want to understand what this particle is, not just that there is a particle. We want to think about what is the symmetry origin of the dark matter particle. Why did it have to be there? So is it extra dimensions? Is it supersymmetry? Is it something else? Okay. And last, although this gets little airplay, although it's increasingly doing so, there's, of course, the question of, is the dark matter composed of one particle species or many? All these questions, what is its mass and spin, how does it interact, of course, assume that there is an it and there's just one of these. But there's absolutely no reason it has to be. And there's some very well-motivated particle frameworks where you have two-component or more-component dark matter. Now, these are all sort of, I would call, particle physics questions. And then, of course, there are other questions having to do with cosmology and astrophysics. So how and when was it produced? I would call that a sort of a cosmological question. In what cosmological era was it produced and how? Why does the dark matter have the observed value? Can we link it to some other known quantities? And then more astrophysical questions. What was its role in structure formation? How is dark matter distributed now? These are, of course, central to astrophysics and really can't be answered compellingly unless you answer all these other questions too. Dark energy and baryons I won't talk much about, but of course there are very interesting questions there. People always talk about the fact that we don't understand 95% of the universe. I would claim it's really more like 100% because we really don't know what baryogenesis mechanism is being used here. Okay, so the dark parts at least, the problems appear to be completely different. So dark matter, no known particles contribute. That's very easy to recognize, and I'll just go through that very quickly in the next slide. It's probably tied to the weak scale, and that probably is basically based on a dimensional argument, which I'll also review for you. But I think there are very strong reasons to think this is an interesting scale for cosmology for dark matter. And of course, the fact that it's going to be probed in the next year and following years is, of course, very interesting. And there are several compelling solutions. So I hope that I can convince you of that. There are many ideas where if we actually found out that they were right, people would say, well, you know, that made sense all the way back in 2008. That would have, you know, that's not a surprise. Dark energy is completely different. Here, the problem is not that no known particles contribute. All known particles contribute through their zero-point energy. And it's not a question of why there is any, it's a question of why there isn't more. It's probably tied not to the weak scale, which is experimentally accessible, but to the Planck scale, the scale of gravity, 10 to the 19 GeV, which means, of course, that the experimental relevance, or the relevance of experiments to this problem, is much less obvious. And I would say that there's no compelling solutions here. It's completely different from this case. There's nothing over here where you could say, this is likely our reasonable explanation of vacuum energy cosmological constant. So what is the purpose of this slide? It's to justify the fact that I'm basically going to ignore this for most of the rest of the talk, although there'll be one slide where I come back to it. But pretty much, I'm going to treat these as different problems and then focus on dark matter. Okay, so dark matter, just let's go through this exercise of understanding what we know about dark matter and why none of the known particles work. So here are the known particles. Famous Fermilab cube. There's the quarks, up and down quarks. Here are the leptons with the electron and its heavier cousins, the neutrino, and the three flavors of neutrino. And the force carriers, the weak bosons, the strong gluon, and the quantum of electromagnetism, the photon. And you can then compare these to the known dark matter quantities. The first known dark matter property is that it's gravitationally interacting. And that is, of course, satisfied by all of these. And is completely useless for constraining what the dark matter is. Second point is that it has to be long-lived. It can't be something that flitted in and out of existence. And so that eliminates all these things which have very short lifetimes on the order of lifetime in the universe. So those are gone. And it can't be hot because we know for structure formation it should be cold or possibly warm. So that eliminated, for example, neutrinos. And last, it can't be baryonic because BBN. Okay, so I think you know all these things well, and as you saw, everything is X'd out. And so there's just no question that if this is a particle, this is not any of the known particles. And so this is unambiguous evidence for new physics. In fact, although people talk about fine-tuning and things like that, the first point is that in particle physics, the dark matter is, I would say, the best evidence that the standard model is incomplete. And there's just no way around this. It's not a question of 5 sigma or aesthetic principles of fine-tuning or anything like that. It's simply this just doesn't work. Okay, so now let's get into the heart of this talk. So dark matter exists. It isn't anything we know. What is it? Well, the observational constraints that I just showed you on the previous slide are no match for the creativity of theorists. This is a fact. And in fact, the question whether there's more candidates than there are theorists is a good question, actually. Probably a fewer candidates than theorists, but it's kind of close. Here is a plot from a recent dark matter heat map subpanel report. This is a mass in GeV, and just, although you might not be able to see it, each tick is 3 orders of magnitude. Okay, so we're talking about, 60, 50 orders of magnitude here in mass. And this is the interaction cross-section with ordinary matter. And again, each tick is 3 orders of magnitude, so we're talking about 60 orders of magnitude up and down there in terms of how strongly it interacts with the known particles. And then you can take all the known dark matter candidates that have been proposed and plop them down in this plot somewhere. And so starting in the middle, there are WIMPs, weakly interacting massive particles, which are sort of one class of dark matter, which comes in many flavors. And there are the various names: neutralinos, KK photons, baryons, lightest T-odd particle, things like this in here. There are also SUPERWIMPS, things like axinos, gravitinos, and KK gravitons. And then there are, axions are actually quite a standard one also. But then there are other things that are maybe a little bit more exotic: WIMPzillas, black hole remnants, cue balls invented over at UCLA, fuzzy cold dark matter, And of course, there are many other things you can put on this plot. I've just put a few. Well, BMSAC put a few. But the point is that we have really no idea where this dark matter lies in this plane. Now, what I'm going to do, just to put all my cards on the table, is I'm going to talk about these candidates in this talk. And so you should keep in mind that I'm just talking about a small subset. I'm talking about candidates that have mass somewhere in this sort of EV to TeV range. And all of these other ones are perfectly viable. Okay, so I'm not meaning to imply that WIMPzillas can't be. They certainly could be. But I think there are very strong reasons to actually consider these. And so I would say these are, in some sense, the most motivated. And so what I want to do is explain why I would say that and why we're going to spend the next 40 minutes talking about this. Okay, so cosmology tells us we need new particles, but this is no surprise from the particle physics point of view, because we needed new particles anyway. And the heart of the argument there goes back to the Higgs boson. So we know that there's, well, in the standard model at least, there's a Higgs boson, and it has a mass which you could represent diagrammatically as this propagating scalar particle. And we know how to calculate its mass, and there is a contribution from just simply putting a parameter in the Lagrangian which gives a Higgs boson a mass. So that's this thing with the X on it. There are, however, also quantum corrections, and these come from loop diagrams. And so you can draw many different kinds of loop diagrams, but here's one with an electron and a positron in the loop. And you can calculate what that size should be. And you find it comes out to be something like this, where this big lambda has dimensional units, or units of order of mass units. And it is the largest scale at which you believe your theory is accurate to. And so if you believe, for example, that the standard model was accurate, then nothing new happened to it, all the way up to 10 to the 19 GeV, the Planck mass, for example, where we know that something must go different for quantum gravity. But if you assume that large value for lambda, then what you find is that this thing is, roughly speaking, give or take, 6 orders of magnitude, of order 10 to the 34. And this is 1 in those units. So in other words, this thing has to cancel that thing to 34 decimal places to get you a Higgs mass which can do its job, namely to break electric symmetry. And that's considered bad. That's a fine-tuning problem. That's the CaJAGWR problem, and it's unnatural. So long before we talk about cosmology, this is a problem, and there are well-known fixes. Most of the well-known fixes introduce new particles. Well, all the well-known fixes introduce new particles. And they have the property that they introduce a counterbalancing term to this one. So whereas this one has a minus sign, this one has a plus sign, but the terms have this sort of same form. And then these two terms, even though they're very large, when summed together, give you something that's small. And so this new particle could be supersymmetric particles. It could be other sorts of things. But the bottom line is that at 100 GeV, where you need to make these things cancel off, we expect new particles. And this could be supersymmetry, could be extra dimensions, could be something. But this is purely from a particle physics point of view. We need something here. Okay? Now, that, of course, is interesting. So we've got cosmology, we've got particle physics, both telling you need new particles. But it gets much more interesting than that in 2 stages. So let me tell you the first stage. The first stage is what's called the WIMP miracle. If you have a new particle, which is some heavy particle, and you know how it interacts, you can actually figure out how much of it is left over from the Big Bang. So this is a plot probably taken from Mark's 95 review. But it's a very standard plot of the number density, co-moving number density of some extra particle as a function of time. So initially, in the very hot, small universe, there was just some fixed number of particles in thermal equilibrium. And it's in thermal equilibrium because this process goes back and forth very efficiently. And so there's just some number. But then the universe cools, and you start losing particles because these particles can annihilate to make lighter particles, but the lighter particles aren't energetic enough to make these heavy particles. And so you get this Boltzmann suppression, you very steeply fall down this curve, and you would fall down to absolutely zero and have no extra particles except for the fact that not only is the universe cooling, it's also expanding. And so at some point, although energetically it's perfectly possible for these two particles to annihilate and make FF bar, electron-positron, they can't actually find themselves. There's a sort of geometric suppression factor. And so you don't find another one as you propagate all the way across the universe. And so both directions stop. And you get off this curve, and you end up on some asymptotic relic density curve. Okay? So the essential point is that you just assume that you had a hot universe in the beginning, you started there, and then the rest of this is completely predictable once you know, if you know, the annihilation cross-section, which determines when this process starts happening. Okay, so these are the basics. Now, after you go through a little bit of numerical or semi-analytic work, you can find out that the dark matter relic density is inversely proportional to that cross-section. You know it's got to be that the bigger the cross-section, the smaller the relic density, but it turns out it's just simply an inverse proportionality. So what is the constant of proportionality? Well, let's do the following. Let's take this cross-section, this is units of length squared, and convert it to a mass. Okay, so we just use dimensional analysis. This cross-section has units of 1 over mass squared. And so we have something of order this. So m is the characteristic mass scale of this new dark matter particle. Alpha is something sort of like the electromagnetic alpha, or hypercharge alpha, some alpha like that. And k is a fudge factor I'm just going to put in here, which is somewhere between, say, 1/2 and 2 or 3 or 5 or something like that. Now, if this is what you assume, again, I'm just simply assuming dimensional analysis here, then, of course, omega is proportional to m squared. Okay? And so heavy particles have more left over. And we can actually put in all the bells and whistles and put in all the coupling constants and things like that and get a plot like this. So what is this plot? This plot shows, well, okay, this axis up here is the mass of this dark matter particle, this mass m that enters into here. And this is the fraction of the total dark matter density that would be in this particle. The color coding, the yellow is just shading for 3%, 10%, 30%, 100%. But this band here is the prediction of this relationship here. Okay? So in other words, if I know the mass of the dark matter particle, putting in all the numbers into here, I can get a relic density that's sort of natural given this dimensional relationship. And that would just be a line in this plane. And then that line has some breadth because, of course, there's some fudge factor k, which I don't know if it's exactly 1. It's going to vary over something. And in this case, it was varied from 1/2 to 2. Okay? But the bottom line is that there is a preferred region here relating the mass of the dark matter to the total amount of dark matter. And it's very interesting. If you want the dark matter to naturally have 100%, well, this particle to have 100% of the dark matter relic density, the preferred mass range is between 100 GeV and a TeV. Okay, that's what this is telling you here. If the dark matter, this particle only has to be, say, 10% of the dark matter, then the preferred mass range is between 30 GeV and 300 GeV. But the point is that just purely out of cosmology, you're getting the preference for particles that have of order 100 GeV or TeV in mass. And of course, this fits in beautifully with my previous slide about the fact that particle physics is telling us we need 100 GeV particles anyway. So the WIMP miracle is simply the remarkable coincidence that if you have a particle which has a mass between 100 GeV and 1 TeV, the natural amount of it left over is about 0.1, which is exactly what you'd want for dark matter. Okay? And so, cosmologists always get uppity when I say this, but if cosmologists were really forward-thinking, they would have wanted to build the LHC simply to investigate dark matter, because it's exactly in the right place to sort of find dark matter in the most natural case. Okay, now that was the first piece of really interesting evidence, I would say. The second piece is a little less known, but I think also very interesting. All of this thing that I'm talking about here assumes that the new particle is stable. Right? If it's not stable, all this beautiful numerical coincidence stuff is just irrelevant. It's just not surviving to the present day. You can ask, why should it be stable? After all, what are we considering? We're talking about theories where we have a bunch of standard model particles, photons, electrons, quarks down here, and then some speculative idea for a bunch of new particle states. And invariably, these particles are heavier than the standard model particles. And so what we're talking about is somehow all these particles sort of decay and dribble down to some light particle, but that particle is stable and it doesn't dribble down to the standard model particles. Why should that be? That looks completely unnatural and artificial. The thing is, though, that we actually know something about these new theories. In the ancient history, the last millennium, there was this collider called LEP, and it provided precision constraints on these new particles. Even though we don't know where they are exactly, we know something about them. And to boil down a huge amount of precision work at LEP, here's what happened. Remember, we wanted new particles which couple to the Higgs boson in this way. So they're in these loops, and they're canceling off that huge divergence that we saw in the previous slide. So that's good from the naturalist point of view. But what LEP told us is it's really bad if these new particles also mediate things like this, where you have standard model, for example, E plus E minus scattering to E plus E minus or to quarks or whatever. It's really bad because you can look for signatures of these sort of effects, and you find that they're not there. They're not there, meaning that this new particle had to be, say, heavier than 10 GeV. But that's exactly wrong, because you wanted this particle to be about 100 GeV to make that work. So you have this tension here. You have something you want the new particle to do, and you have something that you don't want it to do, which you might think it always does. The solution was pointed out in a very simple general paper by Cheng and Lo and also by Jose Woodka. The solution is that what you need to do is assume that there's a discrete parity. In other words, that interaction vertices only have an even number of new particles at them. This clearly solves the problem, because then you can preserve all these interactions where you have 2 new particles at every interaction vertex. But you get rid of all these because these have 1 new particle at the interaction vertex. And so just simply assuming this symmetry, this discrete parity, you keep all the good stuff and you get rid of all the bad stuff. And this is the standard method now to build electroweak models, new physics models, which do not violate known constraints. That's interesting just from a particle physics model building sort of point of view, but it's especially interesting from the cosmological point of view, because if you're going to get rid of vertices like this, then if you have some new particle here, you know that it can't decay, because there's no way for it to go to 2 standard model particles. And so it has an immediate cosmological implication, which is that this predicts that not only will we have new physics at the LHC, but it'll be new physics that has a stable, lightest lying state. And the upshot here is that dark matter is now easier to explain than no dark matter, because if you had in a world where there was no dark matter, where the cosmologist observational results told us that there was no dark matter, you would have a problem, because you would try to build these models, you'd find these problems, and you can't fix it with discrete parity, because it's always predicting that there's a stable particle contributing dark matter. So it's exactly the opposite of what many people think. It's much easier to build a model with dark matter in it than no dark matter now. Okay, so this has led to really a burgeoning of activity, which if you are on the AstroPH or HepPH sites, you will have noticed for years. There's been a proliferation of WIMPs. This WIMP paradigm is thriving. And it basically goes like this. So somebody builds a model of electroweak physics to explain the Higgs mechanism or something. Then someone else evaluates the precision constraints, finds that these models don't work, but there are now problems with these models. Someone else then proposes, well, we can fix this with a discrete symmetry. And then everyone jumps up and down and says, wow, that was great, because not only did we fix those problems, we got dark matter out of that. And so dark matter is then sort of coming as a byproduct. It's a great feature of these models. Then you predict dark matter signals like the kind I'm going to talk about in the rest of this talk. And then that plays out, and then someone else builds a new model. And literally, this goes around and around. And there are many examples. I've just given you 4. Well, this one's a little bit of a special case because supersymmetry was proposed, and even the R parity was proposed long, long ago. But it fits into this paradigm if you think about it this way. Universal extra dimensions, where there are new space-time dimensions. These models had problems. KK parity fixes them. Output includes declined dark matter. Brane-on models, well, brane models where we all live on a 3-dimensional subspace. They have a brane parity that leads to brane-on dark matter. And little Higgs models have a T parity, which leads to T-odd dark matter. And the point is that out of all these theories, automatically pops a dark matter candidate, which naturally has the right relic density to be dark matter. Okay, so this is a bit of what's been going on in the field. Now, just to give an example, let me just remind you of the most typical example, which is WIMPs from supersymmetry. In supersymmetry, of course, there are many motivations, but for every known particle x, there's a partner particle x tilde. And some of these x tildes are neutral. There's photinos, xenos, and Higgsinos. And the neutralino is the lightest one of those, or more generally, the lightest mass eigenstate of those. You find that for various reasons I won't go into, it's not at all hard to make this lightest one, the lightest of these 4, be the lightest of all supersymmetric particles. And so very naturally, you get that a neutralino is the lightest supersymmetric particle. It's stable for all the reasons we talked about. It's neutral because these are all neutral. It's weakly interacting, has a mass of 100 GeV, and therefore has all the right properties to be dark matter. And so this is just an example. And again, this plays over and over in these many other examples too. And in these scenarios, the LHC will see supersymmetry soon after it starts running in 08 to 09. It doesn't take a lot of luminosity to actually see this sort of stuff. So just to remind you, the LHC is this huge collider. Center mass energy is 14 TeV. That's to be compared with the tevatron, the current state of the art, which is at 2 TeV. And an even more relevant comparison, I would say, is to think about the number of top quarks that are going to be produced a year. So the top quarks, of course, were discovered not that long ago with just a handful of top quarks. The tevatron is now up to producing somewhere about 1,000 top quarks a year. And the LHC will be producing, 10 to the 7 to 10 to the 9 top quarks a year. So every second there's a top quark popping out the LHC. Just an incredibly huge jump in energy and luminosity. Okay, so what then? What happens when the LHC sees supersymmetry? Well, what the LHC actually sees is not, squark kind of waving to you and going by and telling you it's a squark. What it actually sees is a complicated cascade, typically. So, for example, what you do is you produce squark pairs. Again, they have to be produced in pairs because of this discrete parity. And then that squark then will decay down by radiating off quarks and leptons, etc., all the way down until it can't do that anymore. That is when it reaches the end of the line in a neutralino, which is a dark matter particle. So each squark produces a neutralino, and 2 neutralinos escape the detector, and the signal of that is missing momentum. Now that could be a signal of supersymmetry, but it's definitely not the discovery of dark matter, right? Because you imagine what we're seeing here is we're seeing, here's Atlas, collision in here, off come 2 neutralinos. And what do you actually know about those neutralinos? What you know is that their lifetime is big enough that they got out of the detector, so roughly bigger than 10 to the minus 7 seconds. But we need this particle to actually be dark matter, which means it has to be 10 to the 17 seconds at least. And there's just no way from a detector like this that you can verify this 24 orders of magnitude extrapolation is correct. In fact, there's very simple theories we'll talk about in a second where the lifetime lies exactly in the middle here. So this is not the discovery of dark matter, and so we have to go much farther if we want to actually claim cosmology from the LHC. Okay, so many of us knew this was a problem for a long time, and then we worked on this and have, I think, a pretty interesting way to strengthen the case for dark matter at the LHC. But in retrospect, it all comes back to the standard stuff. It's all basically a repeat of what people have done with BBN. So we weren't as clever as we thought. So let me just give you the BBN analogy, and then you'll see how it applies to dark matter. So for Big Bang nucleosynthesis, you know that if you know the number of baryons in the universe, you can predict, given lots of nuclear physics hitting down thousands of nuclear reactions, you can pin down the amount of lithium-7, helium-3, deuterium, helium-4, various light element abundances, right? And so this is a plot where these bands here are the theoretical predictions as a function of this one variable, the number of baryons. People then can measure the number of light elements, the light element abundance, which gives you these yellow and white boxes. And the point is that those measurements then imply some number of baryons. And the remarkable fact is within, say, a factor of 2, these all predict, helium-4, deuterium, lithium-7, all predict the same number of baryons. And so what has happened is we have theory from nuclear physics giving us these theoretical predictions compared to observations of light element abundances. And the agreement tells us that we understand the universe back to the time of BBN, which is typical nuclear energies, 1 MeV temperatures, in times of 1 second. Okay, so this is a standard pillar of cosmology. What we want to do then for dark matter is to just take this up a few orders of magnitude in energy. We have this beautiful idea that the dark matter is formed through this freeze-out thermal relic density. If we can understand the theory, the particle physics, well enough, we can actually determine the dark matter abundance. We can tell exactly where we should be getting off this steeply falling curve, right? And we can figure that out. What we need to do is, of course, know all this particle physics, which is wrapped up in this symbol here, the annihilation cross-section. But once you know that, you can make that prediction. Then, just as in the BBN case, we can compare this to the dark matter abundance observation. In this case, the abundance observation has been done already for us, so that's just known. And so it's somewhere around here. And by comparing that theory with that observation, we can get a handle on whether this is actually happening. And if it's happening, if you get the agreement, then it tells us that the dark matter that we saw at the collider really probably is the dark matter cosmologically. Okay, so this is the idea. So the question is, how well can we do? Now, as soon as you ask that, you realize that just as in nuclear physics, you had a network of 1,000 equations, 1,000 processes. In particle physics, it may not be 1,000, but it's a lot. And so nicely, Mark and his collaborators have written down all the Feynman diagrams for annihilation of dark matter. And you're not supposed to actually see all the details. What you're supposed to be impressed by how many there are. So you see, for example, well, you can't, but let me tell you, neutralinos can annihilate through a T-channel fermion to fermion-fermion. Okay, and that fermion and these fermions can be anything. So this could be up quarks or electrons or neutrinos, any of those things. And then there's diagrams with Z bosons and Higgs, CP-odd Higgs bosons. There's neutralinos in here. There are charginos. There's all these different things. And the point is, if you really want to be able to pin down the relic density prediction, you have to measure every single parameter that comes into these diagrams, or check, be confident that these things are so negligible that you don't have to know what they are. Okay? So this has to be done, and in the end of the day, although you might start, you can sort of see, well, the dominant thing is going to be this diagram, blah, blah, blah. At the end of the day, what it comes down to is you actually have to experimentally measure basically all the masses and interactions of all the superpartners, unfortunately. Okay? Now, how do we go about measuring things with precision at the LHC rather than just discovering supersymmetry? Well, it's a very detailed and model-dependent story. So remember, here is the squark cascading down to a neutralino and radiating off various quarks and leptons. What you have to do is start reconstructing this cascade chain. And you start forming various Lorentz invariant quantities, invariant dilepton masses and things like this. Here's just an example of, out of a chain like this, you can form a bunch of quantities. And you start looking for these edges. Okay? And so this is the lepton-lepton invariant mass. And you see some distribution with a sharp drop-off here. And that drop-off is corresponding to some algebraic combination of the masses entering into this cascade. And then, of course, there are many masses entering into that cascade, so that doesn't help. But if you gather together enough information, you can actually get more measurements than there are uncertainties or unknowns, and you can actually solve for these things. Okay? So that's kinematics leading you to mass measurements. Of course, cross-sections lead you to coupling measurements and things like this. And it's a very long, involved story. The ILC is the next generation one. And I don't know if Barry Barish ever spends any time at Caltech anymore, but presumably you all know a lot about this. For here, the relevant thing is that the ILC is a very clean collider, and it has collides E plus E minus, and it has a variable beam energy. So the nice thing about it is you can, instead of having to start by creating squarks up here and having them cascade down and having this huge complicated cascade chain to work out, you could actually start down here if you need to and just make leptons and have them 2-body decay and sort things out there. So you can just work yourself up the decay chain starting here. Once you've sorted out everything down here, you can then produce these guys, then get a 2-step cascade, then go up there and get a 3-step cascade. And so basically, this allows you, along with several other things, including the polarization of the electron beam, to actually sort out things with much higher precision and much less model dependently. Start date, if it's built, I'm pretty confident about these 2 digits. Those 2 are not certain, and news is not good recently. Okay, so to make a long story short, a group of us in the American Linear Collider Physics Group, Cosmology Subgroup, decided to carry out this program and ask how well can one actually pin down the relic density using collider measurements. So here's a plane. So we picked a particular model, and we can talk about which model this was later if you like. But we plotted results. Here's the mass of the dark matter particle, and here is the theoretical prediction of the thermal relic density based on collider data. Okay, so you use collider data, and then you follow that relic density curve and see where you end up. Now, first starting with the known facts, WMAP and related current cosmological data tell us the relic density to within, plus or minus 8%, say. But of course, they tell us absolutely nothing about the dark matter particle. We saw that that varied over 60 orders of magnitude, and could be more. So there's nothing to say in this direction, but it does constrain us to this region here. The LHC, using all that precision analysis that we talked about just before, can actually confine you to this rectangle here, where you can actually claim a measurement. Well, this is pretty unambiguous, actually. A measurement of the mass of the lightest neutralino to plus or minus 5 GeV. But the really amazing thing is not just the mass, but that you can actually constrain so many other processes that you can actually determine the relic density to plus or minus about 20%. Okay, and so this, of course, was a model chosen where the dark matter got the right relic density. So this overlaps here, but you could imagine you could get an answer which just completely doesn't overlap by orders of magnitude. Okay, so this is really quite a precise confirmation of the WMAP result. Now, of course, by the time that comes around, there will be improved cosmological observations. Planck with maybe plus or minus 1 or 2% on this. And if everything goes well, here is what the ILC would be able to do in terms of these measurements. It can pin the mass of this particle down to about 50 MeV and can actually get a comparable precision to Planck on the relic density, plus or minus 2%. Okay, and so this is the results at, I should say, at one particular supersymmetric point, LCC1. This, as is indicated here, is the best case scenario. Okay, it's a beautiful model where everything is produced at the LHC and things are pretty light. But it is an existence proof that there are cases, perfectly valid supersymmetric models, where you could actually compare microphysics and cosmology at this level. Okay, so let me try to explain then what that means. The first thing would be, of course, to compare the collider and the cosmological measurements or predictions of omega. If they're identical, if you really find that you have a 1% agreement between this theoretical particle physics prediction and the observed cosmological value, I think you could say, congratulations, you've discovered the identity of dark matter and extended our understanding of the universe to 10 GeV when the relic freeze-out happens in times of 1 nanosecond. And of course, this is really pushing back our frontier quite a bit from BBN, about 9 orders of magnitude in time. Of course, life might not be so simple. There is the possibility that these don't actually match up, right? So are they identical? No. Well, which is bigger? That's the first question. And if you found that, say, the omega collider was bigger, well, that's telling you that the thing that's produced at the collider has an apparent relic density bigger than the dark matter relic density. That can't be. And so the obvious question is, well, does it decay? If the answer is yes, and you can somehow verify that, well, then calculate the new omega and take this route. And if that turns out right, then congratulations, you can go over there. But if it doesn't decay, well, maybe there's some sorts of entry production that diluted this thing in the early universe. You might still get over there. If that doesn't work, you might have to go to some non-standard cosmology. If, in fact, the cosmological omega is bigger, then the question is, well, maybe what I have is a multi-component theory of dark matter, where one of the components is this thing we got out of the LHC, and the other component is something else, maybe like axions. So can you discover the axion that contributes also dark matter? If yes, well, great. Figure out what that relic density is and try to end up over here. Then you have 2-component dark matter. If no, well, maybe you made a mistake. Did you make a mistake? Yes. Well, fix it and end up over there. You didn't make a mistake. Are you sure you didn't make a mistake? Yes. Then things are hopeless, and then you might as well work on dark energy because it's all over. So this is the kind of thing that actually might happen. We might be doing these sort of flowcharts in 5 years. Well, it's kind of your personal taste, right? So, for example, in BBN, things don't actually exactly line up either. But we're all pretty sure BBN happened at least at some level, right? So it's the same sort of thing here. Clearly, the better the precision between this comparison with that, the more inclined everyone's going to be to say that this is not just some numerical coincidence that actually happened in the early universe. But probably everybody's breakpoint varies. But I would say, for me at least, a percent level comparison would be fantastic. Okay, so let me skip this slide. Well, okay, let me just mention this. Another interesting thing that we can do with the relic density experimental analysis is to note that this whole relic density is, of course, determined by a Boltzmann equation, which has that the number density has two effects. There's the effect of making and annihilating these dark matter particles over here. But then, of course, there's just a simple dilution effect from expansion, characterized by that Hubble. And what we're saying here is that we now have the possibility of having a window on the universe at temperature of 10 GeV. So by doing this, in everything I've talked about so far, we've assumed the standard value or function for h. Okay? And that gives us some results. But of course, another way to say it is by making this comparison of the relic density with the prediction, we can actually probe non-standard contributions to the expansion of the universe. So that, in other words, the Friedmann equation, you can entertain the possibility that it's not just simply this standard part over here, but it's got some extra bit in here. And this is work actually in progress with Sean Carroll here. But what we've done is just simply parameterize extra contributions to the Friedmann equation with delta rho, some new energy density contribution, which goes as temperature to some exponent n. And this is not the most general, of course, possibility, but there are a variety of reasonable things you could think about that work in here. For example, varying G Newton just amounts to taking n equals 4. And other things can be put in this framework. And basically, the results are here. For some value of n, if you can check that delta omega h squared is less than 10% or something like that, you can constrain the amount of strange energy density that was present in the universe at 10 GeV. So to something like 10% or something like that. So this is not all that profound, but what it's just saying is that when you now have a window on the universe at 10 GeV, you have a very strong lever arm, and you can constrain all sorts of things that might be absent at later times. How many minutes are we here? 10 more minutes. Okay, I just want to say a couple things about how this relates to other WIMP searches, and then we'll talk about SUPERWIMPS. So the WIMP properties are pretty much set if they're WIMPs. The velocity is about this. It's about 1 per meter. And of course, people are looking for these in underground detectors. So this is a plot which is already a little bit out of date. It's just really irritating because every 2 weeks this plot gets out of date. There's a lot of progress in this field. This is the WIMP mass here. This is the interaction cross-section for spin-independent interactions of the dark matter with nucleons. And the shaded stuff here is the theoretical predictions from supersymmetry. Okay? So there's the general supersymmetry with this whole thing filled in. And then there's some sort of prettier models which have these brown things filled in. These are these minimal supergravity models. And the contours here, dashed and solid, are the current and future probes. So there are two competing and very exciting technologies, CDMS representing the cryogenic side, and the liquid noble gases represented here by xenon 10. So these are the current ones, and actually now CDMS has published, as of, I guess, a couple of weeks ago, ones that are actually quite competitive or even a little bit better than xenon 10. So this is the contour that's out of date. But anyway, the point is that they're getting very interesting results which are getting close to the sort of heart of the theoretical predictions. And if you let them speculate about a couple of years from now, the Lux 300 kilogram sort of successor to xenon 10 is expected to get down to this green line. The CDMS 7 super towers, 25 kilograms, goes down to here. And this is really beating down the bounds of the sensitivity by 2 orders of magnitude. Now, from a theorist perspective, I'd like to just point out that this is extraordinarily interesting territory here. Because although I can't go into detail about it, there are many, many models which predict 10 to the minus 44 here. And there are very good reasons for it too. So minimal supergravity, focus point, gaugino-mediated, more minimal, 2-1 model, split supersymmetry, all these, which are motivated by all sorts of crazy ideas, all actually end up predicting cross-sections right in here. So at least from my sort of supersymmetric frame of mind, this is not just any old 2 orders of magnitude. There's an extraordinarily exciting 2 orders of magnitude that are being covered in the next year or two, or a year or more here. Well, okay, so if you actually do see something, of course, it's extremely interesting too, because not only does the LHC tell you about the relic density, it also tells you where you ought to be in this plane. This plane, all these contours, well, all these experimental contours assume that dark matter has the standard sort of isothermal halo sort of distribution around us. And of course, that's an assumption. The point is that the LHC and the ILC can actually tell us what the cross-section should be for scattering off of photons. And this is actually the point with error bars of the accuracy of that measurement, at least for this best case scenario. And the point is that by comparing that with actual event rates at direct detection detectors, you can learn then about the local dark matter density, velocity profiles, and really ushers in the age of neutralino astronomy. So this would be the end goal, and it would really allow you to fix the particle physics and start understanding astrophysics. Okay, so that was all about WIMPs. Okay, and many of you would be perfectly excused if you said, I told you there's lots of different kinds of WIMPs. Many of you could say, well, we don't really care because they're just names and they're astrophysically identical. Right? They're all weakly interacting. They're all cold. They're all stable. So it has really no astrophysical implications what kind of WIMPs they are. Now you could say, well, is this true of all dark matter candidates that they have these properties? And the answer is certainly not. We saw a huge variety of dark matter candidates. But what I've tried to emphasize here is that WIMPs have a sort of privileged place because they are motivated by this thing called the WIMP miracle, this very natural occurrence that the relic density is just right without having to tune anything. So you could say, well, there are other dark matter candidates, WIMPzillas and things like that. But we don't like them because they don't have the WIMP miracle, and so effectively all good dark matter candidates have these properties. Is that true? The answer is no. In fact, that's not even true. There's a whole other category, which I will spend the rest of the time talking about, called SUPERWIMPS, which have every good virtue of WIMPs, but which have completely different implications for detection. In fact, all these are different. Okay? So how does this work? How can you actually have the WIMP miracle work with something that, for example, has no weak interactions? So, okay, so let me give an example of how it can work. So supersymmetry has a partner particle for every known particle. There's a particle called the graviton, and supersymmetry predicts that there's a spin 3/2 particle called the gravitino. In the simplest supersymmetric theories, this particle, just like all the other superpartners, has a mass of around 100 GeV. It's different from them, though, of course, because it inherits the same couplings that the graviton has. Supersymmetry does relate the couplings, although not the masses. And so the interactions are only gravitational for the gravitino. So they're much, much weaker than weak. Okay, they're all suppressed by G Newton. Now, there are two possibilities. Either this gravitino is not the lightest supersymmetric particle. Okay, so there's something else over here, like a neutralino, which is the lightest supersymmetric particle, or it is the LSB. In this case here, the gravitino has very little relevance because the standard model particles are produced, say, at colliders, and they will decay down over here, and they will decay to the lightest one here. They're kinematically allowed to decay to this one, but that just never happens because this is so weakly coupled to all this stuff over here. So in this case, the gravitino is totally a spectator and has nothing to do with any of the collider phenomenology, or in fact, most of the cosmology. And this is the assumption in most of the literature, is the assumption of WIMP dark matter. However, this is a perfectly viable possibility. All these things have sort of 100 GeV masses, and so this one could just be, 90 GeV, and that could be 100 GeV. It could be lighter. And what we'll see is that this leads to completely different cosmology in particle physics. So what is the difference? Well, so suppose these gravitinos are the LSPs, the lightest ones. The early universe has basically no change to it. There's some WIMP, which freezes out, and the fact that there's this gravitino interacting with G Newton is completely irrelevant. However, at some point, this WIMP travels along for, a long time, thinking it's going to be the dark matter, and it's setting itself up to nuclear galaxy formation, things like this. But at some point, it can't help the fact that there actually is a possible decay to gravitinos. And so then all the WIMPs decay to gravitinos. And this happens, you can calculate just using simple dimensional analysis what the time is for this. It turns out that it happens after somewhere in the range from seconds to months. Okay, so it's a long time by particle physics standards because there's this huge M-Planck suppression to this decay mode. But of course, it's fairly early in the history of the universe. The bottom line of this scenario, then, is that these gravitinos inherit the right relic density. The WIMPs froze out with some right relic density. They contributed some reasonable fraction to the gravitinos. However, the dark matter, then, only has gravitational interactions because it's gravitinos. So it's super weakly interacting dark matter. It's not WIMPs anymore. And there are many concrete realizations of this. I've talked about supersymmetry, but there are also extra-dimensional realizations of this, things like quintessinos, excinos, etc., which have been explored by many, many people. And they all sort of have this flavor. So what does this mean? Well, this has a lot of interesting implications. Let's just talk about the LHC phenomenology first. What it means is that this particle is not the dark matter, right? So in particular, it doesn't even have to be neutral anymore. So it could be that this particle here is, say, a partner of the electron, a selectron, which has charge. And so the implications for the LHC are that what we may see when the collider turns on is not missing energy, where all of us, we're just getting neutralinos that are missing, and we see missing PT. In fact, what we may see are heavy, long-lived charged particles streaming out of the detector. Okay, these are lifetimes of a second or a month, so effectively infinite, stable for the detector. But they can be charged even though, because they're not going to end up being charged dark matter. They're going to decay. So this is an example where if you assumed that this particle was actually stable just because it left the detector, you'd be wrong. And its actual decay is happening out here somewhere. Now, this is very interesting. If you actually have charged particles leaving, first of all, the discovery prospects for the LHC are much improved because this is much more striking than just missing energy. Well, second of all, you can actually trap these. So these particles have charge. They ionize things as they get out here, and they could actually be stopped in the detector or in some trap that you set up outside here. And we and others have done studies about asking how many of these particles could you trap. And it turns out if you have a meter-thick sort of slab of water under the detector, you could catch maybe 1,000 of these per year. Okay, so it's not millions, but it's pretty good. And now if you can catch these, of course, what you would do is you would take these, your water, you catch these, open a little hole here every so often, let them drip out, and get them into some underground reservoir, ship them off to, Gran Sasso or Super K or something, and watch them decay. And you could actually wait for a month deep underground where there's no muon background and just look for these decays happen. Okay, so what did we learn from that? Well, it turns out the decay lifetime is a very simple function of parameters. It has to depend on the gravitino mass depends on this lepton mass, and it has this Newton because everything is mediated by gravity. So it's got G Newton in here, and that's it. And so if you could actually measure, for example, this lifetime, so you just do an undergraduate physics experiment where you're just looking for, an exponentially falling curve. You measure the decay time, tau. You measure the lepton mass from collider kinematics. And there's a 2-by decay. You measure, say, the monoenergetic energy of this lepton. You get 3 constraints, and you can actually back out and get the gravitational mass. And you can even get back out G Newton. So the point of this is that you could actually measure a gravitational strength interaction at a collider. It's commonly said that you cannot possibly probe gravity in a particle physics experiment because it's just too weak. It usually is too weak, but if you can sort of get where you want by just waiting a long time, you can actually do this. You would actually measure G Newton on fundamental particle scales, so you can tell that a 10 to the minus 27 kilogram thing is interacting with another one exactly with the Newtonian force. And what you would get out of this is actually the quantitative verification that this particle here that's missing is not just any random particle. It has to be the thing that is interacting with the gravitational strength, almost certainly the gravitino, and that would be a precise test of supergravity, and strongly suggests string theory is not just a dream. It does other things too. I won't talk about them since it's getting late. Now there are all sorts of cosmological interesting properties of this scenario too. What we're talking about, remember, is the scenario where dark matter is produced by 3s out, survives for, say, a month, and then explodes and decays. Right? So it decays to the eventual, the real dark matter particle, and then something else, like a lepton or a photon. This is happening well after BBN. And so the first question is, does it mess up all of the beautiful triumphs of BBN? And this has taken on a life of its own. There's a huge amount of work on understanding non-standard BBN with these late decays in it. And I think the jury is still out, but there are some indications that not only, well, it's certainly not ruled out. There are parameter regions where it's not ruled out, but there are even indications that it might actually help with the lithium-7 and maybe even lithium-6 problems. Those of you who know the BBN story know that the beauty of BBN is now a little bit sullied by the fact that the CMB has so precisely given us the amount of baryons that now this lithium-7 number looks a little bit out of line. Turns out with late decays, you can actually fix this discrepancy. And so that's an interesting possibility. Another thing is that these late decays, in some cases, dump electromagnetic energy into the universe, and that can distort the CMB. So of course, the CMB, as far as we know, has a beautiful black body spectrum. But if you throw a bunch of photons in, highly energetic photons, late in the universe's history, that is around a month, this gets distorted. And they go by the name of mu distortions, and you can calculate how big those are. And they're a little beyond current bounds, but not much. And probably one of the most interesting things is the impact on small-scale structure. What's happening now is that you don't have a dark matter particle that is just sitting there from 1 nanosecond on. You have it produced in late decays with large velocities. Okay, so the actual dark matter, that is the SUPERWIMP or gravitino, is actually produced at a month with some relativistic velocity. And you can imagine then it's not really cold, it could be warm. And so this suppresses small-scale structure, at least as determined by theorists like me, that is parameterized by lambda free streaming, or this phase space density Q. And this has all sorts of interesting effects, has been investigated by many different people. Here's a plot from Manoj Kapling-Hat, where basically he's plotting the power spectrum for a variety of things. So cold dark matter is here, sterile neutrinos, sort of the classic warm dark matter, are here, and then for a particular SUPERWIMP model, you have SUPERWIMPs doing something like this. So the point is that they can actually disrupt small-scale structure just like stereo neutrinos, but you don't have to postulate any strange KeV stereo neutrino. It's just standard supersymmetry, which you swallowed already if you were going to believe in WIMPs, but with a slight twist on it. So basically, you get warm dark matter with a cold dark matter pedigree. Okay, so these are just some of the things that could happen with SuperWIMPs. Let me conclude. So particle dark matter is as well motivated as ever. If we had ever any reason to believe that WIMPs were the dark matter, now is the time. This is based not only on just this WIMP miracle, but the LEP precision results really motivate that too. And there's been a proliferation of candidates because it's just so easy to build WIMP dark matter models. There's many more WIMPs have been proposed in the last 4 years than in the previous history combined. There's also this possibility that it's SuperWIMPs, which are interesting because they're really qualitatively different. It's just not a different name on the same thing. You can have warm stuff, metastable, only gravitationally interacting dark matter from the same particle physics theories that WIMPs had. If dark matter is WIMPs or SuperWIMPs, colliders will certainly produce it. So the LHC, all the stuff I've been talking about, will see supersymmetry and will make these things, often in the first year, but certainly in the first 3 years, assuming everything works. May identify it as dark matter by this thermal relic density argument, and may allow us to really open up a new window on the universe at a nanosecond. So really pushing the BBN sort of frontier back to thermal relic freeze-out. So the bottom line, I guess, is that, of course, everything, all this theory stuff is speculative until experiments turn on. The great thing is that experiments are turning on. So the LHC begins somewhere in the next academic year, maybe starting in the summer. Direct detection is really improving rapidly, and as I tried to emphasize, is covering some interesting ground. And indirect detection, I just left out of this talk, but it's also a similar story. There's also some interesting prospects there. So this field will be transformed soon. Of course, I don't mean that dark matter will be discovered soon, but the best candidates will be discovered soon. So 5 years from now, either they will be under active investigation or we'll know that all those are wrong. And I guess that counts as transformation too. But anyway, I hope it's the former, of course. That's it. Thanks.